So first we're going to start with shortwave radiation, and we're going to think about how much of that radiation is considered direct radiation. So there's a relatively clear path from the sun itself down to the earth with the shortwave radiation, and then that's called direct radiation. But there's also diffuse radiation, and there are different processes that take the sun's rays and scatter them, such that for a given part of the earth, let's say a tree, that you might have radiation that's coming in from all directions. And in that case, we consider that radiation to be diffuse. Now, also, that diffuse radiation is essentially reflected radiation, and there are different things that reflect radiation and scatter the rays. So if we take a look at an ecosystem, some of that radiation that's coming in from the sky is going to be relatively direct, but there's also going to be radiation that enters into clouds and gets reflected or refracted, and that changes the angle of it. And so for a given spot, for example, right here you can see is relatively brightly lit. A lot of that is brightly lit from direct radiation, and there are darker areas too that are underneath clouds, but they're still going to get a lot of radiation. But instead of being direct, it's coming from all different directions, and that's diffuse radiation. And so at any one point on the earth and at any one time, there's different amounts of direct and diffuse radiation. Now, part of where this becomes important is also thinking about albedo. Albedo is the property of a surface to reflect light. And pretty simply, a white area reflects a lot more shortwave radiation than a dark area does. And so snowy areas tend to be pretty white, and they're going to reflect a lot of the sun's rays. So that would have a relatively high albedo, as opposed to dark areas, like this body of water, where a lot less of that light is going to get reflected and more of it will get absorbed. Whether an ecosystem reflects or absorbs light is also dependent on its structure. And there's also something associated with this called the albedo feedback. Now essentially, there are differences in albedo that happen over time. So there's lower albedo midday than at dawn or dusk. And so if you think about if we have a surface and during the day, early or late, the angle of the light is relatively low. And that means a lot more of it's going to get reflected than actually if we have midday direct radiation. And so we actually have lower albedo midday than at dawn or dusk. And part of that has to do with the way that leaves are situated, for example, and whether light's just going to bounce off them or get trapped in a canopy. In addition, you'll have lower albedo during cloudy than clear, and the reason for that is the same general principle, that during cloudy we have a lot more diffuse light, which means a lot more diffuse light is coming at a relatively low angle than in a clear day, when more of it is coming from an angle that's perpendicular to the surface. So the authors also state that the amount of long wave or thermal radiation emitted by an object depends on its temperature and its emissivity. So the idea here is that shortwave radiation comes in, and a portion of that is going to be absorbed, a portion of that is going to be reflected. The amount of energy that's absorbed by a surface, so we have shortwave radiation coming in, some of that gets reflected and stays shortwave, and some of that gets emitted as long wave. And we tend to think of this as thermal radiation because it's a lower energy, longer wavelength. And the amount of long wave radiation emitted by an object depends on its temperature and its emissivity. So to take that statement, we can put that into our net radiation budget. So the net radiation associated with an ecosystem can be characterized as the difference in shortwave radiation coming in and out, and you add also the amount of long wave radiation coming in or out. And that's one way to generate what your net radiation budget is. Another way is to think about it in terms of albedo, and then also differences in temperature and emissivity. So what this equation shows on the right is essentially the net radiation budget is first dependent on the difference between shortwave radiation in and out. And another way of writing this portion of the equation right here is to say, well, if you take a look at the amount of shortwave radiation coming in and then calculate the albedo, the net radiation budget is 1 minus the albedo times the amount of shortwave radiation coming in. So if you have shortwave radiation coming in and a portion of that is reflected, the amount that's absorbed is going to be based on the albedo and the amount of shortwave radiation that you have coming in. So if you have a relatively high albedo, so let's say it's 1, it's perfectly reflective, the net radiation budget is 0 because 1 minus 1 is 0. So there's no net absorption of energy. But if you have a low albedo, something close to 0, then 1 minus 0 is 1, and almost all of the shortwave radiation is absorbed. And we'll put some numbers on this alpha in just a second. So alpha equals your albedo. All right. So the second part of the equation is really thinking about the long wave energy balance, and it's a different representation of understanding how much long wave radiation goes in and comes out. And the way that you can say this is that you're going to have a constant here, and the specific constant doesn't matter. But essentially, if you want to think about what determines how much long wave radiation comes in and out, it's due to the differences in the temperature of the surface and the sky, and then the emissivities of the sky and the surface. So basically, if you have a cold sky and a hot ecosystem, so let's say this is our sky right here, and this is your ecosystem there. If that temperature differential is high, such that this is really hot and this is really cold, on a net basis, you're going to have a lot more, I should have drawn it like that, long wave radiation that flows from the hot surface to the cold surface. So you're going to have a lot more energy being released from hot to cold. In contrast, if this is cold and this is cold, the differences in temperature between the sky and the surface is a lot lower. And as a consequence, the amount of radiation that flows, long wave radiation that goes from this cold surface to the cold sky, is a lot lower. Now there's variation in the temperature of the sky, for example. And one of the things that are important to know is that clouds are warmer than space. Now hopefully I'll have a video in a little bit that shows you some of the differences in temperatures of clouds and clear sky. But essentially, when you look up in the sky during the day or the night, you'll have clouds and then you'll have clear sky next to it. And these are cold, the clouds, depending on where they are in the atmosphere. But these tend to be pretty cold, but the sky is a lot colder. And so if you're ever out in your sleeping bag at night and camping under a cloudy sky is going to be a lot less cold than under a clear sky. So in this case, the long wave radiation balance is going to depend on part on surface temperatures, temperature of the sky and temperature of the surface, which gets modified by the emissivities, which is an efficiency of transfer. And that efficiency of transfer modifies the movement of long wave radiation between the surface and the sky. As it turns out, most of the absorbed radiation is emitted, and those emissivities are close to 98%. So in that case, long wave radiation balance depends on the differences in temperatures. So when we think about how much long wave radiation is lost from an ecosystem, for the most part, we have to know what its temperature is, or its surface temperature at least, and the temperature of the sky that's above it. And the difference between the two determines that radiation balance.